Hi everybody. So in this video I want to talk about the transition elements. The transition elements or transition metals are those fellows that fall into this group here. Now you might remember from an earlier video, this is where we're filling in the d orbitals. Now for the transition elements, let's just write that out. So the transition elements, or here I'll call them the transition metals, they have partially filled d orbitals. So the d orbital can hold 10 electrons. And the transition metals or fellows are those elements where the d orbitals are not quite filled. So that would take us from, if we're in this fourth row here, from scandium out to copper. So that means that zinc and cadmium and mercury, those would ordinarily not be considered transition metals because those are at D10. So remember here we're filling in, over here we're filling in the 4s orbitals, and we're putting in 2 electrons there. We're coming back down to the third shell here to fill in the 3d. So it's 3d, 1, 2, 3, etc., all the way out to 10. So up to copper, the Ds are partially filled. And the thing about those partially filled electron orbitals, they're very close in energy to one another. It's a little bit easier to move electrons from one d orbital to another than it is to, say, to move from an s to a d or an s to a p. And so that gives the transition metals a certain character to them, and probably helps induce a certain amount of metallic bonding. But they don't always have to have metallic bonds. There's one other aspect of the transition metals that I wanted to discuss. So in mineralogy, you'll notice that a number of these, like manganese and iron and cobalt and nickel and copper, a lot of these have a 2+ charge. So if they have these very messy, partially filled d orbitals, and if those d orbitals are close in energy to one another and it's easy to move those electrons around from one d orbital to the next, why is it a 2+ charge is so common? Now we should qualify this. One of the characters of the transition metals or transition elements is they can take on a lot of different charges. So iron can be +3, titanium is usually +3, it could be +4, chromium is +3. So there are a lot of different charges that are possible for these elements. But 2+ is very common. And to understand why the 2+ charge is common, we need to just take a brief look at the way we note electrons. Now, the way we note electrons or electron shells is that we take a look at, let's say, well, let's take iron as an example. If we want to fill in 26 electrons to balance the 26 protons in iron, we would have to fill the K shell and the L shell, and we're going to start filling in the M shell. So we'll put 2 electrons in here in the s orbital, 6 electrons in here, and then we'll get the argon structure. When we reach an argon structure, that's a noble gas structure, and we will usually notate that as argon with square brackets around it. And then for the N shell, and let's just number these, 1, 2, 3, and 4, we start filling in the 4s, then the 3d. Now here we're going to put the 4s last because that is the outermost shell, and we're going to put the 3d in here. Now how many electrons are going into the 3d? 1, 2, 3, 4, 5, 6. So we're counting 6 over to get to iron. So for iron, for the neutral atom, so iron with 0 charge, it would have this kind of electron configuration. It would have an argon structure plus the 3d6 and the 4s2. Now notice this is not in order of energy. These 4s electrons would be filled first before the 3d6. they're at a lower energy level. So here in this type of notation for writing out electron orbitals, we usually put these in order of the quantum numbers. So 3 goes before 4. But take a look at this. We have these two 4s electrons that are sitting out here. And if those were to be pulled away by some element like oxygen, and oxygen is happy to take on a 2- charge, so it's happy to take on those 2 electrons, then iron would be left with a 2+ charge. But notice that there's nothing really special about iron in that first row of D elements. So let's take a look at manganese. If we have the element manganese, then it would similarly have an argon structure added to that. On top of argon, we'd still have the 4s2, but instead of 3d6, it would be 3d5. But here, for this 2+ charge, the number of d electrons don't really matter. Again, we have these two 4s orbital electrons that are happy to be taken away by some other atom, such as oxygen, which has a very high electronegativity. It's happy to grab up 2 electrons. So manganese can also have a 2+ charge. And that can happen with any of these. It can happen with zinc or copper or nickel, and it does. With some of these, once the 2+ charges are gone, the other anions like oxygen or fluorine or chlorine, etc., might start digging away at some of the d orbitals too, and you can get a so-called higher valence state or a higher charge. But the 2+ charge happens to be very common because we have these 4s orbitals that are sitting out there that can be easily grabbed by an oxygen 2-, which, by the way, is the single most common atom in the Earth's crust. The crust is made of mostly out of oxygen. There's more oxygen than any other element. It's really the most abundant element in not only the crust, but also the mantle. And so there's plenty of oxygen around to grab up those unwanted or not so heavily needed 4s electrons that are in the outermost shell of those transition elements. So we'll see that a lot. When we start looking at mineral formulas or oxides. We'll see things like copper oxide and iron oxide and manganese oxide, etc.